You're live. All right, let's go and check out.
It's the X, it's the lightweight desktop.
Okay, the access to the one. It's a card.
This, I just inherited this one from my wife. I tortured her for a little while.
And then you did the right thing with
I tortured her for a while with
Arch Gen 2.
But then it's still like it would just run like overheat on Windows 7. So it did better when I put it in a virtual machine. I let Linux runs it wasn't enough memory. So found it all and
Got the files up for it though?
And I've still got her VM right here. It's got it's like an OEM version that's got a pass through down to the BIOS. It's a lot of work to save that.
I would have just taken off the files and put the Linux on.
Yeah, that's
Like,
what I'm going to do.
to be honest, Linux Mint is much, like it's very simple.
Yeah, but she's not. I mean, she's not. Trying to use Microsoft Word.
LibreOffice. Download LibreOffice.
I could have tried it, of course. Why does it have to use
The Wi-Fi guest
Testing, testing. Testing, testing. Okay.
also XFCE isn't really with Wi-Fi. Yeah, it's not really good at detecting Wi-Fi and setting up passwords on it. I usually use GNOME.
Use what?
GNOME. GNOME.
So I guess I just have to type it in.
Guess, I don't know.
Get a bucket.
I got a couple there, yeah.
I'm going to the bathroom.
Anything else?
I'm good, man. We're live?
Still on.
What's the name of here?
Pub Forge Guest.
Like just, I'm not the technical, so it's a technical name.
No.
It's like CFP. What a concept.
It's like so much flour.
All right, everybody. Well, it is 6:30 on the dot, so we get started at 6:30. And so I'll thank you all for coming out. Welcome to the first Lancaster AI meetup. Yes. Woo! First one, all right. So I just wanted to say thank you to a couple of people who have helped make this possible, because it's not always the easiest thing to get meetups started in the area. But thank you to Joel, who's in the back there at Industrial Resolutions and also runs PubForge, for giving us the space to be able to meet today. Thank you very much, Joel. I want to thank Suji, which is a home AI-based company that works with disabilities like Alzheimer's and autism, who helped get some of the refreshments for us today. And my name is Rich Everetts. I'm the kind of the organizer for the event, and I also co-founded Suji as well. So with that, I'm not sure where Wes is yet, but he'll be here momentarily. He promised me he'd be here. So just kidding, sort of. He's going to be talking later on. He's doing the advanced talk, which is on using AI in production. So you get to see how AI is being used at a company that is a Series B level startup. So there's some great stuff that Brand Yourself is doing on the back end. Basically, if you're not familiar with Brand Yourself, it's a company that scans all of your social media and is able to determine whether you are have a good brand or not, essentially. And it gives you a score, and you're able to adjust things and improve your brand. And there's a lot of AI involved, both visual recognition as well as language processing. So I'm really looking forward to that talk. So for me, I'm going to get you guys started on some basic neural networks. All right? So what I want to be able to discuss today, who here has familiar with neural networks? Like, who here has worked with them at all in any form? Kind of? Okay, well. All right, awesome. Well, then this is great, because this is an introduction to what we're doing. So neural networks. I'm going to talk today about the most basic neural network out there, which is called a perceptron. Now, before I get into that, I want to be able to talk about what is the abstraction, like why do we use these neural networks? And to understand that, we actually have to talk a little bit about biology. Neural networks, so it's based on biology. So let's take a look at how a neuron actually works. I know this is like 7th grade science class, you know, going back where you're dissecting animals and stuff like that. But we're going to take a look at some neurons and stuff and to understand the biology of what we're doing. So if you guys remember, a neuron kind of looks something like this, right? And it has this thing that kind of comes down here. And this is the cell. And then you have these things coming down, what we call an axon. And you have these little things coming out here at the axon terminal. And up here you have these dendrites, which are connections from other neurons coming in. Okay? So what ends up happening, if you remember with neural networks, is that you have all this like electrical impulses coming in through here into the neuron. And what ends up happening is it kind of wavers as you're sending in impulses, and it decides whether to fire or not. Well, it reaches this thing called a threshold, an activation threshold. And once that activation threshold is hit, it spikes, the electric signal spikes, and it does what we call firing, where it fires that signal down there out through these axon terminals into the other neurons and connects with other neurons. And then it comes back down like this and goes through the process. Pretty simple stuff there. So let's actually take a look a little bit more in depth. You have an input, and then you have your output. Now, the interesting thing is that these inputs and outputs, they're not actually connected to each other. There's this little thing here called a synaptic cleft, which is between all these connections here. And you have these little things called ion gates, which are right here in between them. And it works all on ionization. Okay? So what happens is the electrical signal, as it comes through this myelin sheath basically keeps the electrical signal from firing off into a million different locations. Okay? It's a great insulator as it comes down here, and it actually speeds up the connection. Because one of the things you got to remember is that these neurons, some of them are really long, especially motor neurons. They go really far in your body. And so to keep that signal focused and shooting down, they have this myelin sheath. So it actually shoots down here, and it comes down the side of this thing, and as it passes through here, it changes it basically opens the gates, just like you would find in a silicon system, right? It opens these gates. And what happens is that as it changes that, if Ca2 plus, I think, is what it is, it's a positive ionization, there's these things called vesicles. I know this is getting technical, all right? But it is really impressive to figure all this out. You have these things called neurotransmitters, which is how the information is actually getting passed between these. It gets sucked into these gates. And you have this process called exocytosis, where it breaks basically these vesicles, and the neurotransmitters, which are these proteins which carry information, get flooded into here and are pulled into here because of the difference in ionization, and the signal, that's how the electrical signal gets passed. It really is an amazing, absolutely amazing process about how it actually works together, okay? Now, the reason that we wanted to take a look at all of this is because it's important to remember how absolutely stunning this process works. In 1 cubic centimeter of your brain, there are more connections than there are stars in the Milky Way galaxy. It's pretty impressive and how all this works together. Now, we're not mimicking this exactly, okay? If you want to mimic a neuron exactly, you're going to want to look into things like neuromorphic computing or mem-resistant computing, which are more focused on exactly duplicating the biological nature of inside, okay? We're not doing that here. What we're doing is we're focusing on inputs, outputs, and changing the information as we go between them, all right? So that was a nice little biology lesson, which is always exciting. All right. Okay, so let's take a look real quick. We have an input, an output, and we got to adjust the signal somehow. All right, we're going to use this little dial here. I know it looks like a bird beak, but it is a dial. Okay, so we have an input, we're going to call X, an output, we call Y, and this here, which changes the signal, we'll call W, which is a weight. How much of that weight do we let through? Okay, this is the simple as you can get. So in order to figure out what Y is and what the output is, we take our input, which is X, and we times it, multiply it by the weight. It's a pretty simple standard relationship, right? Which is Y equals X times W. X times W. So if this is 8.5 and your weight is 0.1, then your Y is going to be 0.85, which is a prediction. So we're going to say 8.5 times 0.1 equals 0.85. It's pretty simple stuff. There's nothing really hidden here. There's nothing too extraordinary. What you end up finding here is that this is what we're going to set up a binary classifier. So we're going to set up we decide whether something is or is not something. Is it a win or is it a loss? It is a yes or is it a no? Is it a dog or is it a cat? Is it a hot dog or is it not, right? You remember that from Silicon Valley? You make $1 billion from that. Okay, so Y equals XW. So if you look at it on a graph, right? Maybe you can't see that, so let me make it bigger for you. A binary classifier takes information. You have a graph that looks like that. You have a bunch of points there, and you have a bunch of points here. A binary classifier will go right through the origin in this particular instance and divide them up and saying if it's above here, then it's this. If it's below here, it's that. Okay? This is what Y equals XW looks like when you graph it out. Okay? The thing is that when you do y equals xw like that, it's not very useful. I mean, in my example, 8.5, what if that was the number of toes that a baseball team has on average per person, and we were trying to predict whether they were going to win a game or not? There wouldn't be much relationship between these. It would be kind of pointless. So if we wanted to be able to predict whether a baseball team would make a win or not, we have to add more weights, more inputs, kind of figure those out. So now we're starting to get a little bit bigger. So let's say this is the number of toes on average per baseball player on that team. And let's say this is their win-loss record. And let's say this is fans in the stands. Okay? And this is either win or a loss. Well, we're going to connect these out. And just like all the other ones in a neural network, we're going to have to adjust the signal to describe the relationship between one and the other. Okay? Describe the relationship. So number of toes. Let's say that we're going to start with 8.5. And one loss record, let's say 0.65, because they win 65% of their games. And fans, let's say in thousands, there's 1.2 thousand in the stands. It's like a terrible team, okay? Well, here, let's say maybe this has a relation, a weight of, I don't know, 0.1. And maybe this has a weight of 0.2. And this has a weight of 0. How would we figure out what's the probability that they would have a win based upon these inputs times these weights there? Well, it's a simple addition, right? 8.5 times 0.01 is 0.85. 0.65 times 0.2, which is difficult to see there, I apologize, is actually 0.13. And 1.2 times 0 is 0, which gives us a probability, a 98% chance that they're going to win based upon these inputs. And then we would calculate out our error and everything like that and figure out if we were wrong or not. But this is the prediction this network would make, be 98%. Okay? So let's actually take a look at the math of this. I'm going to try to shrink this out a little bit, sorry. So it is our input. So we have our x1 times the first weight. And then we add this weight here, or we times this weight by this weight, right? So that was our x2 by w, our weight, second weight. And then we had our little guy down here, which was our number of fans, right? It's x3 times the weight of 3. And when we added those up, we got y. This is basically what we did. I hope you guys can see that back there. All right? So this right here, we with math, we like to refactor things, right? What I want to do is I want to create a formula here for you, because if you get into neural networks and you start working on white papers and stuff, you're going to see a lot of fancy formulas, and they're really not that fancy. They just want to look smart, okay, is really what it comes down to. So if you can figure out what they're actually saying, then you'll be able to do some stuff here. Yeah?
Y equals sum of x and w.
Right. So you might have seen this, and I apologize if it's not very good, but it's kind of like this. It's the sum, right? Sigma. Thank you. So in all of these, we have an x and we have a w. And then it's like a list, right? So sum means we're going to start with an index. And where does the index start? 1. We're going to go through a list. And this right here is to n. So technically, we could have, if we had 500 of these, this formula would still work for 500 inputs, right? Because we could just put a 500 up here. In this instance, this is actually a 3. So the sum from I equals 1 to 3 of xi times wi, right? That's what this fancy formula is for a perceptron. Now, the interesting thing is that we're actually missing something. This works great for most instances, right, in a binary classifier. If you're going to program this out, you don't really need to know this. Just be aware of that, okay? There's libraries and stuff to take care of this stuff for you, so don't let it intimidate you. It's just good to know, all right? But there's something missing. So let me give you an example. Let's say you have a nice little graph, okay? And it's, you have the number of coders on the x and the hours to your deadline. And you want to find out, are they going to have a merge conflict or not? Maybe that's what you're kind of come up with. Okay, that's your classifier. Well, if there's only one coder, right, there's a chance that, you know, he doesn't, or she doesn't start till maybe, you know, down here. Okay? But maybe then you have, so these are good guys, but then you start having bad things up here. Okay? Now, y equals mx goes through the origin, right? It always goes through the origin, but it's not going to be able to divide those in two. Like, you're not going to be able to divide them by sticking a line through here, right? You actually need to create a line like this, kind of, right? So it's like this. You actually need to move your lines around. And so what we do is we add this thing. It's a small little thing. It's called a bias, which helps you isolate variables, right? So now you could if you know, y equals what is it? I'm just going to put xw. It's actually y equals mx plus b, but remember that from your math classes, right? Well, it's the same thing here. It's xw, and then we add a b in here. So really, this helps you move this line around and classify. It helps you isolate variables. So this right here is actually the formula for binary classification. That's a basic perceptron, which was discovered all the way back in the 1950s. So it's been a long, long time. And it did have some limitations because you couldn't create what we call an XOR equation, which they proved. And they were like, these neural networks, they'll never be anything. And so they're basically put on a dustbin for almost 20 years until, you know, people started looking at them again a little bit. But that's really the basics of a perceptron, binary classification, what we're doing. So what I like to do here is I'm going to show you some code so you can kind of take all this abstraction and put it into some real data. So let me get this out of your way. And I'm going to do this on the fly. So there might be a couple of errors, which will be fun.
Forgot semicolon on line 12.
Well, we're using Python, so we don't have to worry about that junk.
That would be even funnier.
All right. So I'm going to have to adjust this since I don't have a cameraman for our live feed. In case you didn't know this, we are actually streaming live right now. Actually, yeah, a little bit. Okay, great. So we're going to use NumPy, and let's we want fancy colors. All right, fancy colors. All right, so let's set some variables. Let's set a bias of 0.01 because we want something really simple. And let's set our toes as a NumPy array. And we're going to start off with 8.5, 9.5, 9. And we'll give somebody 10. How's that sound? Okay, win-loss record. We'll create an array. And we will do 0.65, 0.5, 0.7, and 0.8. And let's put a 0 in there just for readability. Okay, what else do we have? We have our fans. And we'll create a NumPy array. And we will do 1.2, 1.8 or 6, 8.4, and 9.3. Okay. And we're going to need to create, what's our first input going to be? Well, our input is going to be a NumPy array. And in that NumPy array, we're going to add the first value in toes, the first value in the one loss record. Oops. And then we're going to do the fans, the first value there. Okay. So let's define our function. What are we going to call it? We'll call it a, let's do something, perceptron. Yeah, that's how you spell it. Okay. So perceptron took an input, right? It takes an input. It'll take an output. And what else are weights? And it's also going to take a bias, right? And what we'll do is we will create inputs times weights. But how do we do that? Because what we're doing is, remember, we're multiplying vectors, right? We're multiplying lists. So 3 items in a list is basically a vector. So how do we multiply vectors? Well, NumPy has this thing called dot multiplication. All right? If you get into neural networks, you're going to learn linear algebra. You're going to learn matrices. You're going to learn how to multiply vectors of data. Places like Google, NVIDIA, they are creating things optimized to multiply vectors. I mean, it's basically cores dedicated to vector multiplication. And they help speed everything up. So what we're going to do is we're going to create a dot. We're going to call it input dot weights. So we're going to multiply our input times our weights. We're going to multiply these 2 vectors together, right? And then we'll add our bias. Yep, thank you. So if you're not familiar with this, what this is basically saying is value equals the previous value plus the bias. So what we're going to do is we're actually just going to shorten it.
Put it on the top line too, plus bias.
Because dot multiplication will.
Yeah. So I'm going to add it to the end. And then what we want to do is we want to return the value. And then we will, let's call our perceptron. Okay, so what we're going to say is our, I don't know, we'll call it NN, is a perceptron. We'll pass it our input, which is this thing right up here. And then we will pass it the, we forgot our weights, huh? Awesome, perception. Another important thing to have, guys. Good job. 0.2 and then 0.
Very appropriate.
And then we'll pass in the bias. And then we will print the winning prediction is the and then we'll add the percentage. And okay, let's see if this works. So I'm using a virtual environment. If you're using Python and you're building neural networks, I highly recommend you do so. There's a great place you can go to PyImageSearch. They have all kinds of setups for how to set up CUDA, how to set up everything on Ubuntu, set up your virtual environment. I use them all the time, and it is the guy's name's Adrian, and he is awesome. He's got great stuff, so I highly recommend checking him out. And we want to just run Python. What do we want? What's it called? Demo.py. Let's see. Oh my gosh, it worked right out of the gate. So we got our winning percentage of 99%, right? Which is what we wanted. We're gonna win. It only took 8.5 toes, guys. All right. Now, normally we would go back. It's probably not right. We would adjust our weights. We would fix that. I'm not going to talk about that too much here. There's a way to go through and adjust your weights in a perceptron, but really nobody uses it because hardly anybody uses perceptrons. So there is stuff called backpropagation, which will go through and fix a lot of your neural networks, and maybe we'll talk about that next time to adjust some of the weights. But for now, we're just going to keep it simple, and yeah, so that's it. So that's a basic perceptron. That's some of the code there, and that'll be it for now. I guess, what time is it? Perfect. So I'm going to open up for questions. I got about 5 minutes, and then we'll switch over to Wes. And so go ahead and ask away if you got anything. Yeah.
I'm not good at math. Is there a library that I can use?
So it depends on what you want to do. I would highly recommend, if you want to learn something until you kind of pick up some of the math stuff, I would recommend Keras. It's a great intro library for building models and understanding that. Again, I would recommend, I mean, there's all kinds of things you can do. There's books. Things like TensorFlow, they have great online tutorials. And there is a ton of free stuff out there. I was just talking with Wes about this the other day. I mean, there's so much free stuff out there. It's actually almost too much. So just pick something that you like and just kind of stick with it. The biggies right now are Caffe, TensorFlow. Those are your good ones. Keras. Those are Theano's end of life, sorry. Those are your 3 biggies right now, but there's also some other ones like PyTorch and some other ones you can look at too. Yeah.
I believe you're using Atom up there. I run a package in Atom that allows you to run scripts directly in Atom.
Sure.
Is that any different than the digital environment that you use to run the Python scripts up there?
I don't think so.
Okay.
No, you're talking about running the, what's that Bash plugin?
IPython notebook or
Like Jupyter? Or you use Jupyter? Yeah. Jupyter's great. Like, I just didn't want to go through the hassle setting it up here. But yeah, absolutely. Use Jupyter. Whenever you see a lot of tutorials at conferences and stuff, they'll use Jupyter. It's easy to duplicate. Sure. Other questions? Yeah. Caffe, TensorFlow are kind of like backends. Keras is kind of like a front end to like help wrap the models and stuff to make it easy, like an API almost. Is that the correct term, Wes? You would use an API wrapper? Yeah.
it's actually like a language that can use any backend. Like you can use TensorFlow or Theano, and it's like an academic paper that describe almost like regular expression.
Yeah. I like to equivocate it to Keras is like the Rails of AI. Like it's really it doesn't leave much room, for finagling stuff. So, but it's great, very opinionated.
Yeah, they were able to generalize. Makes the machine learning models.
What's that? Yep. Keras.
Isn't that a Pokemon?
Any other questions? Let's check online, see if anybody asked any questions. No, just comments, no questions. Trevor's on there. He wanted. He said to say hello. All right. Anyone else? Yeah.
I don't honestly know the answer to this at all. It's like you have toes, win-loss record, and fans.
Yeah.
But your number of entries, it's like the toes I would expect to be the number of players on the team. The win-loss record I would expect to be the number of games.
Sure.
And fans I would also expect to be the number of games. So, but clearly you don't have 4 players because it's a baseball team, right? So it would be interesting to know, like, mathematically how you adjust to take all your players and turn it into 4 entries.
Yeah, I just chose 4 just for 4 random inputs, but you're right. Yes.
So like you might have a bunch of zeros on the
Yep.
other stuff or
Yeah.
something like that.
Yeah, so like if you were doing a CNN or something like that, where you got to fill out the array so that the array all have the same amount of values. Is that what you're saying?
Right.
Yeah, because sometimes toes. Yeah, I get what you're saying. Yeah. I don't have an answer for that one either.
Yeah, I mean, we'll have to look into that.
Yeah. Cool. Yeah.
Could you explain very basic, like the elevator pitch of a few different AI types, or neural network types, like the recursive, backpropagation, perceptron?
Well, you're talking about model types. That's a really big topic.
Okay.
So the two basic ones I would start off with are RNNs and CNN, convolution neural network, and a recursive neural network. Those are two biggies, and there's been a lot of like break off of those, like faster RCNN and like all these other things. Those are two biggies for language processing and computer vision. So that's a good place to start. Okay, awesome. Well, I'm going to pause for a second, and we'll get Wes set up here on the audio, and thank you. Also, is there anybody here who is from another meetup that wants to talk about their meetup? Anybody want to make announcements? Do you have announcements, Joel?
Top of my head, just shooting from the hip, I guess. There it is. Thursday is we got another new meetup. It's catered towards more of a business clientele, a blockchain business. So that is welcome, but it's not exactly the traditional tech meeting. Let's see, what week is it? Is it February yet? So it's a tricky one because the second Thursday, which will be 2 weeks from now, the second Thursday of February is pub standards. Guess hasn't been. That's the great place. It's the post-conference drink up without the conference. So they're just going to meet other technologists in the area. Show up to that one. Third Tuesday of every month is Tech Lancaster. And there's an ample rows of people right now.
Awesome. All right, Russ, want to come up and we'll get you mic'd up?
Good job.
Thank you.
What should I've got this guy.
Do you have HDMI?
Yeah, HDMI.
All right, here.
This side.
Whatever works.
Had it turned around.
Trevor logged in here. He's like, just stream biases. Okay, thanks.
Spies.
That's going to be saved on there, too. All right, let's get you mic'd up.
I apologize. I invited him.
Who, Trevor?
Oh, yeah.
No, I invited him, too.
Oh, okay.
All right, so what you're going to want to do is pull this up through your shirt and just clip it on there.
Okay.
Try to get it down here so that you're not rubbing it.
Like right there? Or should
No,
it
other
be
way.
flipped around?
There you go, other way.
This way.
No, other way. It's,
Is that not right?
nah, it'll get, let's get you. Let's see.
Okay.
Okay, and then let's wrap this up and
Clip it?
you can put it in your pocket. You can clip it if you want. It's up to you.
Pocket's good too.
Okay.
Okay. Let's do
Now are you going to be,
from slides. Oh, I've got to do my other name here. There's no internet connection. How do I connect in?
okay, it is PubForge Gas, and there's the password. Up on the board, upper left.
Upper left. Giddy Fiction? Hopefully that works. We can play this dinosaur game while that happens.
Did it work?
Now we're connected. I feel like that was unfair. All right. Here we go. View present. Okay. Now just use the right and left key for, we don't have any fancy clickers or anything. Is this side better? Where should I stand?
I'll let you know in a second.
That's a serious camera. I didn't know you, is that your equipment? I don't want to get in the way of my own light.
Well, here's the deal.
Should I be over there?
No.
This side? Whoa. What did I do? What did I do, Rich?
Yeah, because of the way the light differential between this.
Should I stand on this side?
What I'm saying is that no, the cameras can't see you, the people can hear.
That's okay.
Okay, so just letting you know.
Yeah. Okay, so I'm Wes. Hello. Been working on some machine learning stuff at brainyourself.com. We've been hard at work and finally got our product out. So I'm here to talk to you a little bit about my experience with that and, as Rich put it, what worked, what didn't. So just a little bit about myself. I've been always fascinated by computers since a young age. I got into math in school and been working with Brain Yourself for the last 7 years and trying to make a go of this machine learning thing. So just to talk to you a little bit about how we think about this concept at Brain Yourself is we try to bring it down to just the idea of optimization. And when you think about what is a problem that I can solve with this tool, this is such a freaking cool tool. What can I solve with this tool? Well, you have to boil it down to optimization. You have to figure out what is a problem that I can reach the minimum or the maximum of. And so some examples might be classification, like we were talking about before. I put this on here. I don't know if you guys read XKCD, but this is one of my favorites of all time. When a user takes a photo, the app should check whether they're in a national park. Sure, easy. GIS lookup, give me a few hours. And check whether the photo is of a bird. Okay, I need a research team in 5 years. It's like, so to check whether a photo is a bird is a classification task. You essentially have to say, what's the confidence that this photo is a bird? And you need to come up with an algorithm that looks at the pixels or looks at whatever and essentially maximizes its ability to tell this is a bird, this is not a bird. You basically maximize your score on that test. And then you have a function that can essentially change itself to be better at that task. Another random example is the game of Go. So Go is an ancient Chinese game. It was invented 2,500 years ago. It has more possible game states than there are stars in the observable universe, which is just mind-blowing. And how are we going to make a machine that can take this vast complexity and turn it into, I can win every game against you? And this has happened, which is the crazy thing. In 2015, AlphaGo was created. It trounced some of the world's greatest Go players in only 48 hours of training, which is just mind-blowing how that is possible. So this is obviously a very potent tool that we have in our tool chest. Now the question is, how do we apply it? So the way you apply it is you have to come up with the objective function. The objective function is essentially your error function, where you say, I'm going to measure how far away am I from where my function is, where my algorithm is now, where my machine is now, and to where I want to be. So if it's a Go player, it's I'm winning every game is where I want to be, and I'm losing every game is where I am now. And somehow I have to get from point A to point B. The loss function or the objective function measures that distance. It tells you I am 50% away or I'm 100% away. And the best way to think about this is like, I put this graph up here. You've got a lot, most of them aren't this clean. When you try to actually visualize your space of what your optimization function looks like, it is just a wild mountain range of local minimums and maximums on your optimization. And ultimately, the best way that I've heard described how this works is you have essentially a gradient descent where you can picture a blind hiker. He can't see the mountain range around him, but he can feel it under his feet. And he's thinking, I'm going to find the lowest, very lowest part of this mountain range. I'm going to find the very lowest valley that there is in all the lands. And so what I'm going to do is I'm going to feel around me with my foot until I feel a spot that goes a little lower than the rest. And I'm going to take a step that direction. Then I'm going to feel around a little more, and I can take a step. This is sort of what Rich was talking about with the back propagation. Is like you're doing what you can. You're not doing great, but you can sort of feel where it feels better, where you're going to optimize. So that's just an analogy to sort of visualize. And this is the line that you want. You're here. You want to get down into this valley, minimizing, maximizing. It's all optimization. I also have a bullet here. I mean, the optimization itself is optimized. So there's all these algorithms that can actually optimize the process of optimizing, which is really, really wild that, this stuff has happened. So the question is, how do we apply this at Brand Yourself? So what are we doing to apply this? We've got 3 major ways that we apply this at Brand Yourself. Just to sort of give you a high level, Brand Yourself is a platform and a service that helps you look great online. Nowadays, your first impression is online. People are Googling you. They're forming their opinion of you based on that. So what we want to do is help you look really good. So one of the things that's happening now is there are all these algorithms designed to find the dirt, to dig it up from you. Our CEO actually ran into this recently. He was invited to go to MTV for some show opportunity, and they had to scan his social media. And if they find something weird, can risk the opportunity. So he actually used our own software to go through, clean all of his stuff up. That's just like a funny use case there. So some of the stuff we look for, you have a Google result. It might not even be you, but it's not looking good on you. So we help you find those. You might have some flagged social media posts, which would be you said something in 2005 that you maybe shouldn't have said, and you forgot about it, but these machines are going through and digging all this dirt on you. So you want to be able to find that stuff. Flagged images. Your friend took a photo of you. You didn't even know it was posted on social media, but your phone gives you an alert. It says, you might want to check this image Joe just posted of you. You might not like it. So these are the types of things that we're looking at Brand Yourself. And again, like Rich said, classifiers, binary classifiers. That's really what we're focused on here. It's a very simple way to approach the problem. You just say, is it A or not A? It's not even A or B or C. It's just A or not A. And so some of the stuff we might look at, back here with like, is it a desirable Google result or not? Is it an appropriate social media post or not? Is it an appropriate image or not? So how do you build one of these things? There's 4 steps. The first step is the absolute most important step of all. And it was the hardest to learn too. All this math stuff, it feels like that's going to be the hard part. It is not, I'll tell you. The hardest part about your problem is understanding it. Understanding what is the problem that we're facing here, how do we actually define it, and then how do we define our loss function. It all seems way easier than it is. You're like, oh, I've got my great idea. Like, of course, social media posts, it's easy. Some of them are really horrible, some of them aren't. It's that easy, right? No, it is not. It is incredibly difficult. You have to go through so many cases, so we got to understand the problem. We've got to figure out a way to represent our data to the machine itself, to the computer. Like basically take a tweet and turn it into one of the vectors that Rich was writing down. You know, like how do you take a tweet and you turn it into 8.2, 4.6, and 3.1? You know, it's like that is really interesting in itself. Then you have to optimize the machine, which is the whole blind hiker analogy we were talking about. But there's some meta game going on where you basically, you know, not only can you be a blind hiker feeling around, but you can try crazy stuff too. You can like pick up the blind hiker and drop him somewhere else random and see what he does. You know, there's a lot of techniques there. Then you have to get it into production, make sure that it's actually usable. It's not going to burst into flames as soon as somebody tries to use it. So, so I'm going to go through all 4 of these as they applied to our problem here at Brand Yourself. The first thing was understanding the problem. Like I said, it was way more difficult than you think it is. We went through hundreds of thousands of social media posts. And we just hired like a whole round table of people to sit around and go, is this going to hurt your reputation or not? And it was really wild. Pete in the back there actually did an incredible job, like just understanding that problem, understanding what it is that we're even looking for. I wrote it down. I brought my notes. I'm not even using them. But I am going to use them for this one thing because this is an exhaustive list of the stuff that we decided is just what we're looking for. Is insults or hatred, complaints at work or school, complaints about a person or a group of people, negligence or absenteeism, like threats, violence, bullying, drinking, drugs, crime, sex, protected class, financial or sensitive information. And it's like, just coming up with that list was not easy. I'll tell you, it was not easy at all. So then once you come up with a list, you have to look at the examples. And there's so many examples that are just gray area, borderline, all this stuff. So dealing with that was really difficult, especially the fact that we had, I don't know, maybe 10, 15 labelers at some point, people just labeling these posts as one or the other. We were all doing it ourselves. We even tried to get the whole company involved in it. And it is not easy. And what you end up having is, because of all the gray area, you have a lot of disagreement on the labels, which is incredibly frustrating. And so if you're thinking about using machine learning for your problem, that's one thing I would highly recommend. Invest very much up front in understanding your problem, physically going through labeling your data, and understanding your gray area. So aside from that, we had to clean the data. So you've got emojis, you've got people that are creating crazy ASCII art with the new character limit on tweets, you've got all sorts of crazy stuff that's in there. So you have to clean the information, you have to scale it, all this stuff. So the one thing to remember that I would say too is, like, here we are at a talk about AI, about machine learning. It goes without saying, you might not need AI. And it's crazy what happens in step 1 when you start to actually filter through your information. You get, think about it. What is information? It's not data. It's something more special than that. It's more essential. It's within your data that you find the information. And you can reshape your data all day, and the information might say the same. Think about a zip file. You zip your files up and send them to your friend. How is it that that text file can be changed into this much smaller text file without losing any information? Well, the information is a gem, and it's hidden in there. And there's something special about being able to tickle it out to try to make it show itself. And I'll give you a perfect example right here. So these are some data points like we were looking before with Rich, with like toes versus fans versus win-loss record. And it's all here. Well, you can do this cool thing. It's called standardization. You subtract the mean, and you scale everything to unit variance. And it puts the whole, so you can see the scale here, 60, 1200, negative 600, negative 20. We get the whole thing down between negative 6 and 6 and negative 4 and 4. And look what happens. Just by subtracting the mean, we've got a clear separation. Red, green, and blue just sort of popped out of there. No machine learning needed. All you had to do is scale the data. Now, and it's very important to do this as well. And this was pretty easy for our case, but there are a lot of scenarios that I have seen where this is the one thing you have to do. As soon as you don't use machine learning, you just look at, I have a list of tools here You just look at, this is just a small sample of the tools that maths are providing for us and that we can use, and there's so many good Python libraries to help you. You just plug in data, hit button, get bacon, and it's amazing. So like one example that we use, this Viterbi. So dynamic programming is actually, I mean, you could even say it's a predecessor to machine learning. It's a way of optimizing something. So you want to find the maximum or the minimum. Like for example, the bag problem. It's like, I am going to put stuff into a bag. My bag can only hold so much. Each thing is worth it. It's like a robber problem. It's like each thing is worth a certain amount and weighs a certain amount. Which things should I put in my bag? Well, it's a really not easy question to answer. Well, dynamic programming can answer that question for you very, very efficiently. We use this Viterbi algorithm to split hashtags. Think about it. You get a hashtag. You don't want to ignore that information. There's a lot of information in that hashtag. It's got like 3 or 4 words in it sometimes. So how do you split a hashtag? Well, you can use dynamic programming. We didn't need machine learning for that. That's just one example. So moving on. This is a slide for you because you were wondering, what are all the types of machine learning that are out there? Well, there's a ton. And you got to pick the right tool for the job. So you've got a whole history here too. I mean, you've got symbolic is sort of the first. That's like, let's look at the actual stuff here, the words as they are. This is learning, like here's my example for this. We've got the peaks. Pike's Peak. So it's 2 capital letters, Pike's Peak. And the machine goes, I know what this is. This is 2 capital letters in a row. That means it's a proper noun. It knows it has the word peak in it, so I think it's a mountain. And then it learns all sorts of other connections just about the context of where it is. And so it's like drawing connections between things. Think like the Google answers that pop up when you ask it like, how old is Aristophanes? Or like, when was Aristophanes born? And it just pops a year out for you. It's like, that's probably a lot of symbolic machine learning behind that. You've got connectionism, which is all the stuff that Rich was talking about. Neural networks, emulating the connections of the brain. You've got, and the backpropagation is its tool. Computer vision, all that stuff is connectionism. You've got evolutionary, which is really cool. Like if you didn't think that programs could mate and have children, you are wrong. They can, and they do, and it's called evolutionary machine learning. It's really fascinating stuff. You can have an alpha male machine learning program that will dominate and that sort of thing, and then have offspring. It's amazing. It's outlandish, but it's amazing. So Bayesian, I mean, this guy Bayes, he was born in 1701. He basically created a religion around the idea of updating assumptions. So a lot of machine learning is based on that idea of probabilistic inference, of basically being able to take something where you can say, I can't be sure, but I can be this sure. I can be a little sure. And then analogy, which is basically where I focus most of my time at Brain Yourself, using analogistic, I'm not sure how to say it, but analogy-based algorithms, which I have, if you just came here for the pretty pictures, I have a really awesome visual here I'd like to show you of exactly what the type of machine learning that we did at Brain Yourself does. So it's really hard to see here, but there's red dots all around here, and there's blue dots in the circle. Now, you won't believe me, but this circle is actually a linear plane. And the only way you can get a circle out of a linear plane is if you do something crazy, which you're about to witness here. So essentially, these algorithms create what's called a kernel, which is a warping of the plane that the data is on into, in this case, it's a polynomial kernel. So you can see the polynomial, think like a parabola. I mean, it's basically a 3D parabola that we're looking at here. But we were able to bend the space that the data lives in. And you can see all the red points, it's just a projection. This could be a radial basis function kernel or a linear kernel. This is the linear kernel down here. This is the parabola kernel. You could have a radial basis, which would make it a sphere. And what happens is with support vector machine, which is what we're using, you can only create linear separation. Your data has to be linearly separable. So it's a very less powerful machine learning, but it works really well still. So the way this works is the linear separation comes down, and it's able to create a linear slice through the warped space, and it yields this circle that we saw earlier, even though it's actually just a straight plane, which is just fascinating way to do that, I think. So that's one of the tools we're using, support vector machine. It basically uses linear planes, linear, I can't figure out how to get back. How do I get back? View, present, there we go. So some of the other stuff we've used, the latent dirichlet allocation, that helps you group things into categories. So you might say like, I want to create a topic model. I want to have a news site. I need to put everything, all the new news into categories automatically. LDA will do that for you. Self-organizing maps will do that for you. We have variational autoencoders are like, I want to generate a time series that doesn't exist. I just want to create a new time series that's based on that's variational autoencoder. Expectation maximization, similar to the optimization stuff. K-nearest neighbor is very similar to all this. And it goes on, the list goes on. Like I said, there's so many possibilities. So what we did, so step number 2, how am I doing on time? I feel like I'm taking a long time. Awesome. Step number 2, represent your data. How do we do that? How do we take a tweet and turn it into a number? That makes no sense. Well, there's a lot of ways to really do this. And honestly, one of the things I want to point out, one of my heroes in machine learning, he says, many of the questions that need to be asked haven't even been asked yet. Like this stuff is just coming out. Like something that you think that you just come up with could be the next big thing. We don't know. It's like the people just haven't thought enough about this stuff. So this is one really simple way to do it, is you say, let's just take all the bags, all the words in the thing and just put a tally mark if it was mentioned. So you have a vocabulary. You have to limit your vocabulary. That's just because machines have limits. I mean, you want it to train quickly. You don't want to say go and then walk away for a year and come back and, wow, it's finally done training. So you want to limit your vocabulary. So you might pick 5,000 or 10,000 of the most common words in your data set and say, these are the words I'm going to look at. Or you might even take off the top and just ignore some of the more common words, which is something that people do. So, so this is an example. Here's a movie review. And you can see the illustration of the bag of words, which is essentially it loses the word the word order information. But we don't care about that. It doesn't matter. It works just as well. It's amazing. It's unbelievable. You don't even need to know the order of the words. You can tell just from which words are in there for most cases. So in this case, you have it appears 6 times. You have I appears 5 times. Down here you have humor, have, great, adventure, satirical. You can already start to see like, oh yeah, I guess you can get a lot of information from just which words are in there. One of the other things we do is term frequency, inverse document frequency. So we basically say, okay, so it appeared 6 times. That must mean it's a very important word. No, it doesn't. It appears 6 times in every movie review. So as a result of that, it gets de-weighted a lot. Same with I, the, to, and, etc. So what you end up doing is basically saying, if this word appears all over the place, we don't really care about it. Anyway, just a very simple way to say, how do we turn words into numbers? These are our numbers. You know, these are our words. So we've effectively turned them into numbers. You essentially just pick an order. So you just say like, I don't know, alphabetical order or whatever. And for where Rich was putting in 4.2 or 8.9 for the number of toes, you might put 6 for it, 5 for I, etc. after you normalize it. Another really cool way that we were able to turn tweets into numbers is this thing called Word2Vec, which is unbelievable technology. I mean, this stuff is amazing. So basically, what it does is it just sits there and it reads everything. So we fed it probably 40 gigs of tweets, which were collected in a matter of like 6 days, by the way. Like, the amount of tweets out there are insane. So the wild thing about this is it's able to create a semantic map of relating words together. So yes, you still don't get word order, but you get something special out of this, which is a sort of relationship between the words that are contained within your documents. So this is a perfect example here. You can see towards the left of this particular graph with these selected items, you can imagine all of the words that you know are possibly in this map, but we've just picked a few to show how there's a pattern. So you've got sad, unimportant, ill, negative, loud, unconscious, evil, cold, poor on this side. And then on this side, you've got rich, important, healthy, good, active, happy, positive, high, passion, etc. So you can see there's some sort of inherent relationship that's just popping out of these things. Really, really cool. Some of the other cool things that I've seen with this is like, so this is a cool equation. If you take king on this map and then you subtracted man from it and then you added woman, you would get a vector that roughly approximated the vector for queen. So it's like there's some really cool stuff going on in here. One of the things that we ran into, so like the glove vectors are a pre-trained thing that's actually included in a package called Spacy. If you do want to use this, you could download it in like 10 minutes and have this up and running and just start playing with it with Spacy, S-P-A-C-Y. And what it uses is the glove vectors, which are trained on Wikipedia. And a really funny, interesting thing that we ran into was, well, Wikipedia isn't really our use case. There's some context switching going on here. We've got Wikipedia, which is talking about, like Triceratops or stochastic gradient descent or like whatever biology thing. Then over here you've got tweets, which people are like, they're like, yo, I ate a fruit roll up today or whatever. And one of the things you see all the time on Twitter is F you. They're like, F you. And it's like, and on the glove vectors are like, oh, fu, yes, kung fu, things like that. Yeah, that's what you must be talking about, martial arts. But when we trained our own one of these models, we found that it understood FU much, much better and was able to flag those better and apply that better. So that was kind of cool. One more quick thing about what Rich was talking about. What was it called when you're trying to find a machine that's just like the brain? Neuromorphic, exactly. So HTM, if you're interested in that, I just wanted to add HTM, hierarchical temporal memory. It's by a guy named Jeff Hawkins. Really fascinating stuff. He is obsessed with that idea, and he's proven this exact same theory of the Word2Vec in his own system. And the coolest thing about it is he was able to train it on like 9 different languages, and the word for like all these words in no matter what language happen to show up in the same rough area. So it's almost like a built-in translator, which is just mind-blowing to me. Absolutely mind-blowing. So now the step 3, let's optimize. How are we gonna use our blind hiker to actually get to the minimum possible point on our error rate? How are we gonna take our error rate from every other one I get wrong to I'm getting 99.9% correct? Well, this is a graph that was absolutely instrumental in helping me understand that. And the way to understand this graph is to think of the left side as like let's go back to the Parker bird analogy. It's like I want to tell if it's a bird or not. So on the left side of this graph, each of these gray points is a picture of a bird. And on the right side are pictures of not birds. Each of these gray circles is a not bird. Now, what's in the circle is what our machine learning algorithm says is a bird. The ones that it got right are called true positives. Positive like a medical test. It's like, yeah, positive as in I'm asserting this is a bird. And it's true because correct. These are false positives. So these are things that it said this is a bird and it's not a bird. So those are called false positives because it's still asserting this is a bird, but it's actually false. So you get these two really important numbers. It's hard to see here what's going on with the screen, but you've got essentially the precision, which is how many things did I say were a bird that actually are a bird? And then you've got recall, which is how many birds did I say were a bird? Or like how many of the total bird pictures did I say were indeed a bird? So your precision and recall are your two really big numbers. And it's important to look at those because if your data is lopsided, you will find that you'll get accuracy levels of 99%. You'll be like, holy shit, my model's incredible. I'm getting 99%. But if 99% of your examples are negative, then it could just be marking them all as negative. So it's one of those things you have to look at precision and recall because you'll have 99% accuracy and you'll look at your recall or your precision and see it's actually very low, 40%, 30% even, something like that, depending on your data. So when you hear people talk about accuracy, you always have to take that with a grain of salt because accuracy doesn't actually mean diddly. You really need the precision and the recall. Now, the harmonic mean between the precision and the recall is called the F1 score. And that's what we picked as our guiding metric. If we can just get our F1 score up, we're doing well because that means both our precision and our recall together are coming up. So let's see if I have any more notes here. So the next slide is just our numbers here. So what do we do to optimize it? Well, there's a lot you can do. There's a lot you can do. And really, honestly, we actually had to get the PhDs on the horn and start saying, okay, we're here, we want to be here. So how do we get there? And it just spent a lot of time talking with people who really knew what the heck they were talking about to help guide us towards the right direction. And honestly, most of our problems were rooted in step one. And that's why I just can't iterate that enough is understanding your problem, understanding your data, understanding what you're going to do. That's the most important thing about going down this path. So you can see where we ended up. So we actually started with keywords, which is not a bad idea. And again, you don't need machine learning. Usually you don't need it. A lot of times, you could just run some statistical analysis on your tweets and find out, hey, actually, if we flag keywords, we can do really dang well. It turned out, look, we had 91% accuracy with our first round of keywords that we just pulled out of our ass. This is just the stuff that we thought should be flagged in any way. And we did pretty darn well. 91% accuracy. But look what happens. 25% precision. What does that mean? That means only 1/4 of the things that we said were bad were actually bad. Now, the recall was 62%. That means that only 2/3 of the things that should have been flagged were actually flagged. So that leaves us with an F1 score of 35%. We revised our keywords. Mostly Pete actually revised the keywords. Almost doubled this score. Not really almost double, but 56% went up a lot. Then we were like, okay, let's just get in this. Let's just see what machine learning can do on this thing. We applied a deep learning methodology because the support vector machine that worked on Google results just did not work for social posts. I'm not sure why, but it just didn't work. So we had to bring out the big guns, basically. Just to give you some frame of reference for our Google results, we use the support vector machine. It's very simple. It trained in like 15 minutes. It takes so little RAM and so little amount of CPU power to run that we don't even run it on a GPU. We run it on a CPU. We run it on a Linode. We actually have a couple Linodes that just like, we can run 10, 15 workers on each one at least. And that's just because we don't need more because it's so fast. So ultimately, SVM is preferable because, again, you might not need machine learning. It's very simple. Keep it simple, stupid. In contrast, the deep learning model, it takes like 4 gigs of GPU RAM just to load the model. So like you need a serious graphics card. Like already your 960, your GTX 960 is a piece of garbage for this thing because it doesn't even have 2 gigs of RAM. Then you've got the whole idea of training it. I mean, some of these models, like you hit go on it, and then you just go to bed, and you wake up in the morning, and maybe it's done by then. So a lot more time consuming, a lot more resource intensive. You don't really want that, but sometimes you need it. Look what it did for us. We took our accuracy, well, our accuracy actually stayed the same, but we took our recall way up is what actually happened. So our precision went down, which was an acceptable price to pay for the huge boost in recall. You can see here our precision and recall are kind of like a trade-off. It's like you can have one or the other, but you can't have both. So we traded some recall for precision because we were having too many false positives. We were having customers call up and say, hey, like I've got like 1,000 things flagged and like 10 of them are actually bad. This is a shit product, right? So that's not good. So we needed to increase. We didn't really care as much about the recall in this iteration. We cared a whole lot about the precision. We killed it. We got all the way up to 98% precision, which means that out of 100 things flagged, only 2 were not really worth your time looking at. And you can see we pretty much maintained that high 86% here, but we boosted our recall from 40% to 70%, which gave us an F1 score of 77%. So machine learning did a lot for us, basically. And we did have to pull out the big guns, but that was a big win, I think. And again, we were talking about the different types of machine learning. I mean, we're using LSTM stands for long short-term memory. It's a type of recurrent neural network, which Rich was talking about earlier. For our images, we use a convolutional neural network. It's actually a regional convolutional neural network, so it basically can tell you there's not only a person in this picture, but he happens to appear right here in this diagram. So last step 4, deploy. How are we going to take this and actually get it to our users so that they can use it? Don't underestimate this. It's expensive. It's not easy to set up properly. You need failovers. It was a lot of work to actually get it, once we had a working thing, to get it into production. Right now we have 7 dedicated servers for scraping and classification. So they basically have to scrape your Twitter, scrape your Google results, get all that information, and then classify it. And we only hit max load on those. The other day we had about 2,000 visitors on the site at the same time from Shark Tank Reair. And that actually hit us at full load. But that's just to give you an idea. We've got a deep learning network. It's running like 40 times on these 7 servers. Pretty cool stuff. Let's see. Is there anything else? No, that's it. That's all I got for you. So I guess we do questions now, if anybody's got questions. Not even.
Why didn't you go with the scale for the, like, wouldn't it have been maybe easier to represent, is this a good versus bad versus of like a scale of 1 to 5? Wouldn't that probably have been easier?
Yep. That's where we started, definitely. But what you end up with is you have one person gives it a 1, one person gives it a 6, one person gives it a 3, and like you can do that, and you just sort of average them all together. Hindsight's 2020. So what we ended up doing is splitting it down into 4. So it was either safe, inappropriate, like actually damaging to your career, or I don't know, I'm not going to touch it. Like I don't know. And that worked pretty well. It was like a range, and we still did end up averaging them together. But that's a really good point. I mean, a 1 to 10, that would definitely work too. Very good question.
Yeah, we found the more polar your data is, so if you have a force to say definitely bad, definitely no, or I don't really know, it just gives you a harder line to then run the machine learning on, which we found is helpful because tweets are very subjective, and so yeah, that was one thing that we found helpful.
What was the effect of data, like the quantity of data on your different percentages and stuff? Like when did you say, hey, I need more data versus maybe my models are wrong? Like how did you make those decisions?
That is a really good question as well. More data is almost always better as long as your data quality is good. So I think that was sort of our play. Like we had that huge issue with just the quality of our data, the speed at which we wanted to go, and the amount of data. We're all fighting forces, and we just ended up where we are. But ultimately what you want is you want to move very quickly because you already understand your problem. You've already done step 1 very well. You hire a shit ton of trainers or labelers, people on Mechanical Turk or whatever. You don't have a room of 2 people labeling things. You get a lot of labelers of diverse perspective, and you label a ton of data. And we had tens of thousands, hundreds of thousands even, and we could use more still. But ultimately, it came down to the quality of the data more than the quantity, I would say. To a point. You want at least, for us, it was, I think 3,000 was a good jump point, and then 10,000 was the next big jump point. So you want to think like, for this type of stuff, general rule of thumb, you want at least 5,000, 10,000 examples. But ultimately, newer software, newer algorithms are doing much better than that.
Are you training your algorithm basically as we speak? So is it like still getting better, or did you just stop your model once it got to a certain goodness and just stopped it there?
Yes, so we stopped it. Ultimately, there's a thing called online learning, which basically means that the model is learning as it classifies. And that's a thing. We don't have that, partly because of quality control. Like somebody could flood it with targeted attack, basically, is one problem with that. But that's not really a huge concern, but also it's a lot on the 4th step deploy. Like actually getting that deployed in production and working properly is not a no-brainer. It's very hard to do. So I think a lot of people do this, is you basically keep a record of how people are labeling the data. If they're saying like, oh, this is wrong, they have a little button on the site that says, this is wrong. And if they mark that, that comes back into our data set for a later retrain, and then we can roll that back out.
So my question is, what systems do you have in place to where, let's say, words or phrases that were once not offensive, all of a sudden become offensive to a certain few?
Yeah.
That doesn't just flood the system with a targeted group of people being offended by a few things when it's not to everybody else.
That is a really excellent question. So the way that we actually solve that problem is with keywords. So again, we have machine learning, but you don't always need machine learning. So a lot of what we do is we have a hot list keyword, and basically some news article hits or something happens, and we have like a little admin interface. You can go in and just see like, add that to the list or whatever. In terms of like the machine learning side of it, In general, all of our data that we feed the machine is hand-picked, you know. So something like that, it would have to have been a mistake that we made, like hand-picking stuff. But, and yeah, otherwise we have the keywords that really help out a lot. Go ahead.
Crap, I forgot.
What you got?
So then the second question, I guess, into that answer would be, I'm close to the loss, and I'm
Keywords, hot list.
What are some of the tools you found very valuable?
I'm drawing a blank.
Sorry, what's that, Rich?
What were some of the tools that you used, that you learned, that you found very valuable?
That's a good question. I might go back to this slide just to sort of this stuff. I mean, basically, understanding your data is really hard, and being able to really make sense of what you're dealing with, especially because of outliers and just stuff like this. So any tools like, I mean, through Python, SciPy, NumPy, any sort of analysis tools like that, where I was able to, like, I didn't have to sit there and write, like, understand what standardization is and actually write the code to subtract the mean and put it on the univariance. Is like I could just call standard scalar dot fit transform, you know, and it was that easy. And so I would highly recommend scikit-learn is really probably the single most effective tool that I've found. So like, yeah, you can use Keras to make models, and yeah, you can use faster RCNN to do image discovery, but ultimately when you're working with your data, scikit-learn is unbelievably useful. So many amazing tools in there. It is a vast, sprawling library, awesome stuff. Scikit-learn, hugely recommend that. It lets you do all this stuff that I've listed here. You can get pretty much all of this stuff is in scikit-learn. Really awesome. Or SciPy, one of the two. Really awesome stuff.
Wes, in addition to that, from what I understand, there's a lot of people here who are in school, they're starting learning. You actually started this on your own, right? This was a side project for you, and you ended up taking this to production in a major company. Like, can you describe that process? It might be helpful.
Totally, yeah. So, I mean, math major definitely helped. I always thought, like, I hated math all through school. I just absolutely hated it. I thought it was like so perfunctory and just really didn't excite that side of my mind that likes to think about things from a less just sort of mechanistic way. And so I was just like, math is not for me. And then I got to school and I learned about prime numbers, and I started thinking about this stuff, and I was like, wow, actually, there's a lot more to math than just this put it in the machine, turn the crank type stuff. And then I started to learn more about it, and I realized, like, wow, do you know that math is like the only field in all of academia that not only doesn't have a definition, but has been proven by itself that it's impossible to define? It's like, whoo, wow. And then you get into all this stuff and you start, you know, like all of a sudden linear algebra is like, okay, I can dig some linear algebra if I have to like get through that. So I would say basically just having a strong foundation in linear algebra in the basic math, so that when you're reading through the stuff, you're not like, what the heck is this symbol? Or you're not just sort of skimming over it and going, well, this is clearly not important because I don't need to understand the math to use the library. It's like, no, it really helps to understand that. And ultimately, if you get the math, you can take this paper that is just like incredibly intimidating at first, and you just chew through it really slowly, and eventually you understand it in a way that it's like, I get this now. I finally get this. And not only do I get this, I can apply it here. So I would say that's half of it. The other half of it is just just experimenting. So the first thing that really got me into it was called SVM Lite. And I would highly recommend this to everybody as a track if you want to get into it. SVM Lite. It's old. It's simple. Everything's a text file. There's no Python. There's no languages. There's nothing. It's just a command line. And you can create a text file with very little skills or knowledge and run it through, and it will train in like 5 minutes or less. Sometimes if you have little data, it'll train like that. And they have tons of examples on the website, or at least a few examples that you can get started where you're basically classifying things into science or not science, or for articles, whatever it is. But SVM Lite was fantastic for me. That actually really paved the way. The first Google search result classifier was written with SVM Lite. You remember now?
Yeah, it came back to me. So aside from you guys, like saying you put articles in that might flag new things for the program, besides stopping it yourself, what would stop, say, another person from developing this to have the machine itself start flagging things based on articles it might be? So like, let's say the website that created the article is usually known for creating BS articles. What stops the machine from becoming biased towards that just because it's been fed all that information?
Nothing really. Honestly, yeah, there can be lots of biases. And that's something we found is like for example, SEC.gov, the Securities Exchange Commission. We have a lot of customers that basically they have lawsuits against them. And it's like they might be totally innocent, but the fact that the lawsuit was filed and that they have the SEC.gov like thing. Now, that said, there's also on SEC tons of good stuff that has nothing to do with you being put, but they all have that SEC like format to the PDFs. It's like they all have SEC somewhere on them. And so what ended up happening was we got a disproportionate amount of the good SEC stuff versus the bad stuff because we scraped all of our training data from our customers. And what ended up happening is it will flag SEC stuff even though it's not bad. Just because it goes, oh, this is SEC. I know this is terrible. This is terrible stuff. But it's not. It's really not even 50-50. It's like most of it's very good. There's a few little bad things, but because our training data was lopsided, like you're saying, yeah, so that's a problem you'll run into. And honestly, the only way to overcome that is just curation. Anyway. Anything else? What you got, Pete?
I was going to ask, are there any big or particularly interesting problems that you think that machine learning hasn't been applied to yet, or doesn't think in fact it's been applied to?
Everything. Yeah, everything. What you got?
How do you maintain this?
How do you maintain this? Right now, we are basically just supporting our rollout, which just happened on the 8th, so less than a month ago, and we're all hands on deck on that. So ultimately, we're not maintaining it right. It just is what it is. If it breaks, I just kick it and give it a cookie, something like that. It's like that's all the maintenance we're doing right now. Yeah, long term, the goal is we want to constantly be improving. We especially take into account the idea of new stuff that's happening all the time because we're a reputation company and reputation moves at the speed of the internet, and so it's like you have to stay on top of that stuff. So I think ultimately we are going to look towards those like online learning or towards at least having a cycle where that new data can be factored in quickly and then moved out. We use a process called continuous integration, which you're probably familiar with, is basically just we have scripts that just usher the changes through to the production. Yeah. Am I out of time?
We are out of time. All right. Thank you, Wes.
Yeah. Thank you, Rich.
All right. Well, that about wraps us up here.
Oh my God, you yummy. Freaking nailed it.
So, Trevor, I just wanted to know real quick, how do you pick the features you want to extract from your data?
Oh, that's a really good question. Feature extraction can be done algorithmically now, which is pretty awesome. That's actually what feature extraction is. I think what he's talking about is feature selection, which is another really important part of the process. You have to basically select as much as you can, as much as you possibly can is really the good way to go about it. Then use algorithmic, what's called feature extraction, which basically says, these are useless, these are useless, these are useless, and these really matter in making the determination. So I would say the best way to do it is use an all-inclusive and then have the machine tell you which ones are actually important.
All right, Trevor, I hope you got that.
Yeah.